Alright, so hello everyone and thank you for coming. This is Level Up Game Development with PureScript Native. Can everyone hear me okay? Alright, so today I'll cover from game engine to distribution, the process of using PureScript Native to develop your own games. I'll cover what exactly is PureScript Native in terms of its relationship to PureScript and the path it provides to C++. I'll go over some of the motivations for using PureScript Native versus, say, Haskell or PureScript's more common JavaScript backend. In this talk, you'll learn how to set up a PureScript Native development environment. I'll discuss what to look for in a game engine when using PureScript Native. You'll learn how to create the foreign exports and imports using the foreign function interface. I'll touch upon some of the differences to keep in mind when using a C++ backend versus the more common PureScript JavaScript backend. You'll learn the necessary steps to build your game using PureScript Native. And last but not least, I'll cover how to package up your game for distribution when using PureScript Native. Okay, so let's start from the top and go over what exactly is PureScript Native. PureScript Native is a PureScript to C++ compiler. It is one of the many backends for PureScript. The more common PureScript backend is JavaScript, but there are PureScript backends for Erlang, C, and even Haskell. Using PureScript Native, you can target C++ instead of JavaScript, and interestingly enough, you can get back to the browser using Scriptum. Going full circle, Scriptum can take your PureScript to C++ game and actually compile it to JavaScript. So, by using PureScript Native, you can target both the desktop and the browser. The first C++ backend for PureScript was known as Pure 11. Pure 11 was in development for roughly 4 years until it was superseded by PureScript Native. Keeping up to date with new releases of PureScript, PureScript Native is actively maintained. You can use PureScript Native on macOS, Windows, Linux, and Raspberry Pi. It's written in Haskell and has multiple tests with full test coverage for Mac and Linux to catch any potential issues. Andy, right there, is the project's maintainer and is very helpful and quickly responds to issues and pull requests. So let's now move from the what to the why. So my motivation for using PureScript Native actually started with Haskell. After having released 2 popular GUI applications written in Haskell, I looked to raise the stakes and use Haskell to create a 3D game. Knowing I needed a game engine, I went to Hackers to try and look for one. There were a few candidates. Helm seemed promising, but supported 2D only and appeared to be abandoned. HGamer 3D was also promising. It binds to a year-old 3D as C++ game engine. Unfortunately, HGamer 3D lacks some very needed functionality. So, going a step down on the abstraction layer, I looked at what bindings there were for libraries handling rendering, sound, GUI, asset loading, input, physics, animation, state management, etc. There seemed to be enough to piece something together. For example, Frag, a first-person shooter written in Haskell, uses OpenGL and the OpenGL Utility Toolkit, or GLUT. Still, while piecing together a game engine was tempting, I quickly went back up the ladder as I wanted to ship a game and not a game engine. But maybe I'll revisit that possibility in the future. Anyway, being familiar with game engines out there, it was likely I would need to bind Haskell to C. At first I thought, though, maybe I can avoid this and try to bind something bind Haskell to C++. But I started with C, so having bound Haskell to C before, this would be ideal. So there was Corange, which is a game engine written in C, but it lacked documentation and was alpha. So I went back to C++ and looked at my options. Each one had its trade-offs and generally didn't feel right. Binding Haskell to C is fairly easy, but not so with C++. This is unfortunate, as some of the widely used libraries for game development are typically in C++. I tried various different methods. You can see some of them here, such as extern C, Hoppy, and inline C double P for binding Haskell to C++. They were all valid methods, but they were not as nice as binding Haskell to C. This situation reminded me of trying to bind Haskell to JavaScript. Maybe you're familiar with that. I tried JC, JS, and even Fay. They were nice and got the job done, but I decided to keep looking. It was at this time that I discovered PureScript. So the path from PureScript to JavaScript is really streamlined. I thought I might look to PureScript again for an option, and sure enough, there was a path from PureScript to C++. At the time, again, it was called Pure 11, but this has since been superseded by PureScript Native. As you'll see, there's very little friction to binding PureScript to a complex C++ code base like a game engine. So binding PureScript to C++ is reminiscent of binding Haskell to C. Being able to bind PureScript to C++ opens up so many possibilities, since there are so many great C++-based projects out there. From cutting-edge game engines, you can see on there all the different categories, to robust machine learning libraries. Picking any one of them and gluing on top of it a PureScript interface gives you some distinct advantages. You can leverage many years of software development while at the same time improve the correctness of your application logic. All right, so I went over my PureScript Native sales pitch. Now let me walk you through setting it up. As you'll see, getting up and running with PureScript Native is fairly easy. It's really just a matter of building the compiler, installing a couple PureScript programs, and putting the foreign function exports in place. So the first step is to install the PureScript Native compiler known as PSCPP. To install PSCPP, clone the PureScript Native repository and build the project. PureScript Native is written in Haskell, so feel free to use your preferred method for building a Haskell project. This here, I just happen to be using Stack as an example. Now, if you do use Stack, make sure your environment can find where Stack installs the PSCPP compiler. So you want to modify your path if you're on Linux. All right, so after you've built the compiler, you need the foreign function exports. These exports coincide with the imports different PureScript packages use. Typically, the PureScript packages assume a JavaScript implementation, but this will supply the necessary C++ implementation. So again, here Andy provides us with the exports needed to support the imports. Again, they're not all of them, but they're a good majority for the core library. So you don't necessarily need Node.js to obtain PureScript and PSC package, but if you already have Node, it is one of the more convenient ways to set up your environment. PureScript Native needs the PureScript dependency for the PureScript compiler known as PERS. Using the PERS compiler, the PureScript Native build process generates something called corefn, or PureScript's functional core. Corefn is the abstract syntax tree or AST of your and your dependency's PureScript code. The PSCPP compiler compiles and converts the AST to C++. So once it has the C++, it's passed to a compiler and linker of your choice to generate the executable. PSC package is used to manage your project's PureScript dependencies. So PureScript Native uses it to acquire the sources of your PureScript dependencies, gathering up their corefn, using the PERS compiler, turning that into C++, and compiling and linking the C++ to build your project. So in this step, you'll initialize the PSC package.json file. This file points to a package set. You can point it either to a locally or remotely hosted package set. This file also lists your project's dependencies. Each dependency list must be in the package set. And a package set is a collection of PureScript packages that you or someone else has assembled such that they are compatible with one another. And an alternative to PSC package is Spago. Spago provides the same functionality as PSC package, but with it, you can override an upstream package set instead of having to fork and maintain a package set just to change, say, version numbers or what the package provides. So with PSC package, you install dependencies much like you would with NPM. PSC package will update your PSC package.json file with what you install, as NPM does. You'll need to know the name of the packages in the packages.json file, but PSC package will attempt to help you if you don't have the correct package name. Now, the PureScript Native compiler, PSCPP, can generate a makefile that makes the build process very easy. Be sure to open it and look around to get a feel for the build process. The PSC double makefile is configured to look in your source for your project source files. You can, of course, change this by modifying the generated makefile. Now, here's a little simple PureScript program that prints the word hello to the console. I'll give you a minute to look that over, but it's importing the different modules. You have the PureScript main, log, prints hello to the console. So, using the generated makefile and make, you can either build a debug or release version of your project. The makefile allows you to pass any compiler or linker flags that you need. If you do need to debug the generated C++, you can take a look at it in the output directory. This is the C++ that is sent to the compilers such as G++ or Clang. All right. So here you see the generated C++ for the simple PureScript program I showed earlier. Looking it over, you can see how it resembles the PureScript program somewhat. It includes the headers, which coincide with the imported modules. The namespace main coincides with the defined main module. Inside main resides the PureScript main function. Right. And then you can see the hello string being passed to log. Now log also has a foreign import and foreign export. So this is the foreign function interface at work. And I'll cover this more later in the talk. Anyway, outside the main namespace resides a C++ main function that's at the bottom. And inside the C++ main function calls PureScript main. So that completes the path of execution. The reason for the double set of parentheses is due to log returning a function, which is returned from PureScript main. And I'll go over this during the binding portion. So after the build process is finished, your project's executable will be in the output/bin directory. The output and bin directory can be configured in the generated makefile. And the executable is called main, but you can also change the name of the executable as well in the makefile. Okay, so you set up your PureScript build environment, but now you need a game engine, right? So picking a game engine is a personal choice when using PureScript Native, but you want to make sure that you have the option to control main and even possibly the game loop itself. So some game engines are more like an application than a library framework. You supply your game logic and it takes it from there, particularly the one on the left there. Controls the game loop, controls the main. This is advantageous for the use case, but it can make using PureScript Native awkward. So after having reviewed many different game engines, I settled on Panda 3D. It doesn't try to control the workflow from concept to executable. I originally wanted to use Godot, but I needed the game engine to be more like a library than an application that you augment from inside. And Panda 3D is a real gem, so if you dig around the internet a bit, you'll find some great projects using it, such as this one. Compatible with Linux, Mac, and Windows, Panda 3D is open source and supports the latest rendering techniques, skeletal-based animation, particle effects, physics, 3D audio, and more. So there's nothing there that you would want elsewhere. There's the render pipeline project, which you see up here. It adds physically based rendering, or PBR, to Panda 3D. And this will soon be incorporated into the main project. So I've used Panda 3D in at least a few projects, such as my online book, 3D Game Shaders for Beginners, which has become quite popular. It uses Panda 3D as a platform for demonstrating shader techniques that you can not only use with Panda, but with any game engine framework or library that offers GPU programmable pipelines. So as you're building your game with PureScript, definitely check this out because we'll need shaders. I've also used Panda 3D for Lambda Lantern, and Lambda Lantern is the proof of concept for using PureScript Native to develop games. Its game logic is programmed in PureScript, and it calls Panda 3D routines through the PureScript foreign function interface, or FFI. Eventually, Lambda Lantern will become a full-featured game for teaching functional programming patterns. Each pattern will manifest itself as a physical puzzle, and the player will have to complete the puzzles to advance through the game. Alright, so let's cover how you actually bind PureScript to C++. Binding PureScript to C++ is the process of creating foreign exports and imports, allowing PureScript to call C++ routines. The C++ exports live in the FFI directory, while the imports can live in your source directory. And here's a bare bones foreign export C++ file. It includes the PureScript native header, that's the runtime. It specifies the module name, which will be the same as the module name defined on the PureScript import side. And it designates the beginning and end of the foreign exports. So between the designated beginning and end lives your exports. Each export is a key value in the export's data structure. The key is a string containing the function name. So you see there, exports string ID. The value is a C++ Lambda function containing the function implementation. Here I'm exporting the ID or identity function. It takes a single parameter and returns it. Now, on the PureScript side, I define the example module, and import the ID function stating that for all A's, it takes an A and returns an A. Going back to the earlier PureScript program, I now import the foreign ID function from the example module and compose it with the log function. Doesn't really change it, but this is just to demonstrate the effect. So we've now officially bound PureScript to C++. Right. So here's the generated C++ with the imported foreign identity function. Notice how it's using the example namespace, which lines up with the module definition created earlier. So just like the previous said, it imports the example module, right? And then you can see it composed there with log at the bottom. So to shuttle values around during runtime, the PureScript native runtime uses the boxed type up there. And export definitions can only accept the box type, and they must return the box type, even if the exported Lambda definition has nothing to return. So to return nothing, you can simply return an empty box value, like I do on the bottom there. The big catch here is that you must know the type before you can unbox it, right? So in some rare cases, you may not know the type, and I'll touch upon this later in the talk. So if you see auto param unboxed, you specify the type, and that's param. So you take it out of the box, I guess, and then to box it back up, box type param, and return it. So for some C++ types, you can return the value unboxed. The box class comes with a few convenient constructors for some of the more used types. In this case, the compiler will do the construction for you. So here you see me returning a string unboxed, while the Lambda definition specifies that it returns the box value. This example compiles and runs just fine. All right, so real world, let's look at a foreign function from Lambda Lantern. This export has a little bit of everything. At the top, you can see that I'm exporting a function called withWindow. It accepts two parameters. The first parameter is a box pointer to a Panda framework, and the second is the box anonymous function, or Lambda. For exports that accept more than one parameter, you must curry them. This is why it accepts a parameter and then returns yet another Lambda that accepts yet another parameter. Both of the nested Lambdas capture the variables defined outside of their scope. This is indicated by the ampersand inside of the square brackets. Right. The first nested Lambda captures by reference the framework variable, that first one there. And then the second one captures by reference both the framework and the f variable. So that's the pointer to the framework, and that's the Lambda function. So notice how the actual procedure itself is wrapped in a Lambda that doesn't take any parameters. withWindow is an effectful function that runs in the effect monad. So to avoid immediately evaluating the effect or effects, this is why the procedure is wrapped in additional Lambda. So this function is thunked, which delays the evaluation of the effects. And what withWindow does is run a callback with a Panda 3D window. So to do this, it unboxes the pointer to the framework. It opens a window. It assigns a pointer to the window, boxes the window up, then evaluates the callback, and then returns an empty box value. So on the PureScript side, I import two data types, framework and window. I import the withWindow function, which takes a framework, a function, and performs some effectful action, returning no information or unit. The accepted function accepts the window, performs some effectful action, and also returns no information or unit. Here you see withWindow being used in the actual game logic. I pass it the framework and a function that accepts the window, performs some effectful action, and returns no information. So similar thing here, I also have with the with framework, which works somewhat similarly, and then I also set the window, and then we go into with the window, and it runs the callback. So this is the generated C++ for the previous code snippet. Notice how the structure is just a bunch of nested C++ lambdas. So if you do have to dig through the C++, this is what you'll be looking at. It's not too bad. So while you're binding, you have to keep in mind a few differences between the C++ and the more traditional JavaScript backends for PureScript. Now, not every PureScript package will have C++ foreign exports for its foreign imports. This typically isn't too bad, as you can model the C++ exports after their JavaScript counterparts. However, in some rare cases, you may not be able to port the JavaScript directly to C++. For these instances, you have to fork the PureScript package and modify it in such a way that you can create the necessary C++ foreign exports for its foreign imports. Alright, so I came across this case when trying to create an export for really unsafe reference equality, found in the PureScript unsafe reference package. This package is used by a PureScript event, which is a dependency of Lambda Lantern. So, PureScript event gives you a cancellation function when you subscribe to an event. But under the hood, this cancellation function uses really unsafe reference equality to compare subscribers. So, delete by unsafe reference equality, that also calls really unsafe reference equality. If there is a match, it deletes the subscriber from the list. But the subscribers are functions, and comparing function for equality works fine in JavaScript, but it's problematic in C++. In C++, the subscribers are lambdas, and they can only be compared for equality if they capture nothing. And this isn't to say that PureScript event is wrong, as I completely understand the assumption of a JavaScript backend, but still, to make it work for both JavaScript and C++, I'll have to maintain a fork that uses some other mechanism for canceling a subscription. So really, unsafe reference equality relies on JavaScript's dynamic type system. However, we don't have this luxury in C++, right? Because it has a static type system. So when unboxing a box type, you have to declare the type. If you don't know the type, you can't unbox the given parameter since the type is erased from the box instance. So the previous C++ backend for PureScript, Pure 11, you see the type there, any, had a tag system for inferring the type. PureC, a C backend for PureScript, also has a tag system. And it may be worth adding tags to PureScript Native runtime to cut down on the need to coordinate pull requests with possible breaking changes and or having to maintain downstream forks. In any case, I arbitrarily chose double for really unsafe reference equality, as it had no adverse effect when running Lambda Lantern, for now anyway. So, the JavaScript event loop is another aspect you'll have to consider. For Lambda Lantern, I knew I wanted to architect it using functional reactive programming, or FRP. So to do that, I chose PureScript event and PureScript behaviors. PureScript event uses clear and set interval, and PureScript behaviors uses request animation frame. So if you're familiar with JavaScript, you know that clear interval, set interval, and request animation frame are well known to the JavaScript world, but they are completely foreign to C++. So to emulate them, I chose a multi-threaded model. But there was a problem with that. So using multiple threads, I experienced some idiosyncrasies not found when using the JavaScript backend. As you may know, JavaScript, excluding the web workers, has a single-threaded event loop. Each event runs one after the other. That's what you see on the left there. But never overlap or run simultaneously. However, in my implementation, events do run simultaneously due to the multiple threads. So to bring order to the chaos, I had to rethink my behaviors and events and add extra control structures. I plan to revisit the multi-threaded model and convert it to a single-threaded event loop like its JavaScript counterpart. Another consideration you have to keep in mind when using the C++ backend versus the JavaScript one, right, is memory management. So PureScript Native helps us out here somewhat with automatic memory management for the generated C++ code through the use of shared pointers. Shared pointers use reference counting, providing a rudimentary form of garbage collection. So for the C++ you write, though, you'll have to keep in mind all of those problems that go along with that, right? The heap, the stack, leaks, use after free, and other manual memory management considerations. But feel free to use smart pointers and other RAII methods, and or some sophisticated garbage collector to alleviate the burden of memory management. All right. So you set up your build environment, right? You chose your game engine. You bound PureScript to the C++ game engine. You worked out the differences between C++ and JavaScript, and you wrote your game in PureScript. Now all you need to do is build and ship your game. Fortunately, building your PureScript native-based game takes only a simple make command, right? Recall that the PSCWP compiler can generate a makefile for you, greatly simplifying the build process. And here you see the make command for Lambda Lantern. Kind of big, but for the compiler flags, I included necessary header files for Panda 3D, Python, and FreeType. So you can see that up top, that's the compiler flags, right? And that's just asking, where are the headers? For the linker flags, I link in the libraries from Panda 3D and pthread. So here, down there, I tell it where all of the dynamic libraries are. So this make command kicks off the build process, right? And for Windows users out there, know that you can get make using Chocolatey, the package manager for Windows. So the build process involves roughly 5 steps. First step gathers up your PureScript source and the source of your PureScript dependencies. These PureScript sources are compiled by the Perls compiler into CoreFN. The CoreFN is compiled by the PSC compiler, generating C++. The C++ compiler takes your generated C++, the headers you supplied, so if you saw earlier, and generates an object file. Then the C++ linker takes your object file and the libraries for your C++ dependencies and generates an executable you can run. So that's eventually where your game is at the bottom. So to get an idea of the build times, it takes around 7 minutes to build Lambda Lantern from scratch. After the first initial build, it takes around 10 seconds to rebuild Lambda Lantern after having changed its source. Alright, so after building comes shipping, right? The exciting part where you release your game to the world. Thankfully, PureScript Native doesn't add any complexity to distributing your game. After the PSC compiler generates the C++, the involvement of PureScript ends. So really it's just a matter of how do you distribute your C++ game. And I'll cover the process of distributing your game for Linux, Mac, and Windows. First up is Linux. So distributing a game for Linux can be somewhat of a challenge given all the different distributions and their different package managers. And I've used Snapgraph and Flatpak before. Maybe you're familiar with those. These are great for exposure, right, since your game is listed in their app store. However, the most convenient way beyond a simple zip file is AppImage. App images require no installation and no root permissions. If packaged correctly, they're completely self-contained and portable. You simply make it executable and it runs just like a single file. And this is the app image directory for Lambda Lantern. Inside it contains Lambda Lantern's 3D models, textures, fonts, configuration, application metadata, executable, shared libraries, desktop file, and more. All this will be squashed into a single file that can be downloaded and run on almost any Linux desktop environment. So to target as many Linux desktops as possible, I recommend building and packaging your game in a virtual machine running Ubuntu 16.04. This will contain an old enough version of libc. To figure out what shared libraries you need, right? You can use LDD. LDD will recursively find the linked libraries and list them. You could include all the libraries are given if you wanted to, but the nice thing about AppImage is you can include as many or as little libraries as you want. And depending on how you configure the app image in the app run file, the libraries found on the host system will be used if the libraries are not present in the app image. So ideally you include any library that isn't typically found on the average system, and this will give your app image the greatest chance of working outside of the box. So to generate the app image, simply run the app image tool, supplying it your app directory. The app image tool will perform some validation and then generate the app image if everything checks out. Alright, so that was the process for Linux. Now let's take a look at the one for Mac. So packing up your game for Mac consists of putting together an app bundle and creating an Apple disk image or DMG containing the app bundle itself. As it was with Linux, you'll need to determine what shared or dynamically linked libraries your game executable uses. I recommend Mac Dynamic Lib Bundler. This tool will copy the needed dynamic libs into your app bundle and will fix the paths so that your executable can be successfully linked at runtime. So this is the basic directory structure of an app bundle. The info.plist or information property list contains the metadata about your app bundle. So after you've assembled your app bundle, you can turn it into an Apple disk image or DMG installer. Your players can then download this file and use it to install your game on their machine. For creating the DMG installer, I recommend Node app DMG, found on GitHub. Alright, so that covers Mac. Now let's talk about Windows. The process for Windows is somewhat different from the one for Mac or Linux. You'll need to determine which dynamic libraries or DLLs your game requires. Make sure to gather up your game's assets, documentation, license, executable DLLs, and icon. For packing up your game and creating a Windows installer for it, I recommend InnoSetup. InnoSetup comes with a graphical wizard to walk you through the process. Otherwise, you can script it for more advanced installs or uninstall procedures. So, and after you package up your game, right, I recommend distributing on itch.io. Itch gives you a dedicated page for your game, lists your game in its search results, hosts your downloads, and if you're in the business of selling your game, handles all the payment processing. And you can find Lambda Lantern on Itch, and be sure to check back every now and then for updates. Okay, so before I close out, a little bit about myself, right? My name is David Lettier. Professionally, I'm a software engineer specializing in machine learning and natural language processing. In my off time, I write technical articles, software tools, and games. You can find me on Twitter and on GitHub. And while you're on GitHub, check out GIFQuery and Movie Monad. GIFQuery and Movie Monad are two GUI-based applications written in Haskell that I created and maintain. I use GIFQuery all the time for taking short clips of gameplay, which is great for advertising your game on Twitter. And Movie Monad is my daily driver for playing videos. Okay, that's all I have for you. I'd like to thank everyone for coming. This has been Level Up Game Development with PureScript Native. Does anyone have any questions?
Have you attempted to buy into the Unreal Engine at all?
No, but I did look at it like other game engines, more sophisticated game engines, I guess. It likes to control everything. Really, it's like the Hollywood principle. It'll call you, don't call it. So you will have to reverse engineer the sort of how it constructs main, and then you could bind it. Otherwise, like I said, it makes using PureScript Native kind of awkward because PureScript Native wants to control main too. So what you'd have to do is, write out your code, then have it generated, and then delete main from the output. And then you could supply that to Unreal.
I'm not sure about this, but the game Unreal Engine is on GitHub, so you could take it and then you don't have to reverse engineer like all of it like delete afterwards. You can just change the bit.
Sure. You could look at how it constructs main and then bind to that. Because the problem with the other game engines was, right, so to be as compatible and as robust as possible, they try to construct main for all of their various different platforms, even the web. So you have to break that down and then bind and then capture that class that's creating all of that so that you can put it in PureScript's main.
What was the output of the inscripting stuff? I have it running in the web. Is that like writing WebAssembly?
So Scriptum can do ASM.js or WebAssembly. Depends on what you want it to output. You can output both. So what it does is it takes at least with Lambda Lantern, it would take the OpenGL and convert it to WebGL so that it can run in the browser. That's why I thought it was interesting, right? Because PureScript typically JavaScript, but you can go full circle by using a Scriptum. So you could also do the desktop and the browser at the same time.
Can you maybe, too much trouble to know, but I'm just curious, what what it looks like when you're working on a game. Do you have Panda open and you're updating current state of the game, looking at it?
I don't have it on this machine, but if you want to, you can go to GitHub. Just type in Lambda Lantern, it should come right up. And you can see how I built the exports and imports. Really what I just have is the Panda documentation up and seeing, okay, for me to do this process, I need this, this, and this. So I go ahead and just bind it real quick to that and then create the imports, right? And then just start continuing on with the game logic. But, Panda 3 doesn't have a dedicated world builder as other game engines do. For that, it just recommends to use Blender. Yeah.
Are you working on PureScript Panda Polygons library?
So eventually when I finish Lambda Lantern and get it where I want, then I'll just cut that out and create its own PureScript package so that others can use Panda 3D.
You have a Medium article that covers this book as well?
Yeah, so if you search online, just type in PureScript game development or PureScript native game development, should come right up.
Yeah.
And then these, oh shit, go ahead.
Do you know if, so on the JavaScript backend, we can have like FN and functions that correspond to uncurry functions, so like we fully saturate them that regulates the uncurry credential with JavaScript. You experimented at all with C++?
No, but I have to check the PureScript native FFI and the exports, but I don't see why you couldn't write that, right? So that you wouldn't have to go through the more tedious process of having to query it yourself and just call those FN2 or FN3 or whatever. So it should be able to work, yeah.
So, how is Lambda Lantern coming along, and what's it?
Yeah. So I spent a lot of time on this talk, so development has stopped, but will resume after this. So far, I've got some pretty good engagement with it, and people are excited about it. But really, it's just so I'll take different functional patterns, whether it be like functor, applicative, monad, that kind of thing, and try to, manifest it as a physical puzzle so that people could understand it. And then really what it will be doing is there'll be like puzzle pieces on the screen, and you have to assemble them, right, to create the right concoction. And then whatever, release you from the next room so you can go to the next one. But yeah, there's going to be a big update recently because I recently did all the shaders. So it should look pretty modern after this next update, yeah.
Who would you say the game is for? Is it programmers or is it general audience?
I mean, whatever the intersection is of people who enjoy functional programming and also like to play games.
Do you need a programming background? Is what I mean.
You shouldn't, because it'd just be assembling puzzle pieces.
Yeah.
And really, in the end, it's just right. You just need the right type signature.
Do you think like the C++ is derivative at all?
Well, I mean, so with Lambda Lantern, right, it's pretty demanding, I think, as far as applications go. I haven't noticed any like performance issues or any like optimizations it could be doing. It's really just, I mean, everything, if you look at the generated C++, it's just a giant nested thing of lambdas. So everything captures what it needs to, and everything's immutable. So you don't have to worry about, something changing under your feet. And other than that, right, all the heavy lifting is done in the engine. So really this is just like, like a marionette just coordinating it.
Do you write the shaders yourself, or have you experimented with any like shader generation?
So I have tried Lambda Cube, I think it is, with Haskell. They're trying to, create a functional language for generating shaders. But other than that, no, I just write them by hand. So if you go to the repository that I showed earlier, you can see like a multitude of different effects and how that's done. And the shaders are quite small, so I don't know if the trade-off would be great to try to develop something like Lambda Cube, but for PureScript, I guess. I don't know, maybe.
How big is the community? It seems like it's probably not huge, I would imagine. Like,
Yeah, I mean, well, you know, like even with functional programming community, it's still small.
yeah.
So even that is a smaller subset. But I have seen some activity uptick on the PureScript native repository, and Andy, you know, he's always working on it and fixing whatever issues people come across. And I've sort of been advocating it, and since then I see other people being interested in it. I think right now the main blockage is it says it's experimental, and I think that's just to ward off any high expectations. But I have found it to be completely stable. So if you're interested, I'd definitely dive in.
It's, say, like, what you've done is really impressive.
Oh, thank you.
Yeah.
It's a general question. As the PureScript Native backend develops more and more, I guess are there any specific use cases that you think C++ would be better for than maybe other possible backends that might develop at the same time? So I know somebody announced like a few months back, like about talking about a Go back.
Mhm.
So that might be better utilized for something over here that C++ maybe is good for, maybe isn't for that. There's also the Erlang backend. So like, what kinds of things do you think the PureScript native backend would like excel in that other backends from PureScript would?
Yeah, I mean, I can't comment really on the pros and cons of different languages, but what I would say is that you know, if there's a particular library out there or some piece of code base that's giant, like Panda 3D has been in development for over 10 years, I wouldn't want to write that myself. so if there is, you know, some giant library for your project that you want to target, then it's great to have the multiple backends, right? Because you can stick with the same language, but just, you know, sort of multiplex it and target whatever language you have. So in the case of game development, I would say that C++ is going to be your best bet, because almost all of the libraries that you would care about are written in C++.
Do you know if anyone else working on another game?
Not that I know of, no. I think I'm the only one. But the great thing, you know, after I release this game, and then others will say, "Whoa, what's it written in?" And then maybe that will catch on. I mean, if you look at the actual game logic itself, it's pretty small, you know, for what it does. I mean, it's only one level, right? But you know, after the binding happens, you can use all of those, you know, the algebraic types and what to cut down on a lot of the boilerplate. And so the actual game is, I think, is only like 600 lines. So.
Are you collaborating with anyone to come up with like game content?
No, so it's just all in-house myself. So the models and all that. Well, I mean, the music I did grab from someone that supplies it for open license, and the font. That was the only ones that I grabbed out of it. But the models and all that stuff, yeah. All right, thanks.